Okay, yeah, that was a very boomer move of me. So let's see. So today we're going to finish up on chapter 15, which is on lipids. And one thing I should sort of clarify also. Of course, as always with these biochem chapters that have a little bit of a different format from the traditional organic chemistry chapters, I would say by and large, at least for starters, focus on what we cover in class. That's going to be what I'm going to focus on in the exams. True, I do leave some OWL questions sometimes that go a little beyond that. I don't mind adding a little challenge to the homework. I don't mind exposing you guys to other ideas that are related. And I never know if by looking at something that seems at first kind of tangential, you know, I never know how many students are going to go, oh, and understand something a little bit better as a result. So I don't mind doing that. But I don't want it to be 80% of the assignment like that. I certainly try my best. But certainly, as always, focus on what we cover in class. It's like I said, it's not, as they say, it's not rocket surgery. If you were a teacher and you were going to write an exam, what would be the first things you would think of to ask about? Wouldn't it be the things you talked about in class? So it's the same with me. It's no secret. I have no intention of hiding that from you. But we're going to finish the chapter on lipids, going to take you through a few other classes of lipids. And then if you'll indulge me, I figured I'd maybe just ad lib for a few minutes on alcohols before we actually get into the alcohols chapter. That one I've left, I believe, 3 class days for. Let me just double check that. Yeah, we're doing Wednesday and Friday and then the following Monday. Yes, and that's, again, I think that will be enough time. I don't want to rush through that. The alcohols chapter is going to be pretty content heavy, much more so than these couple of biochem chapters that we've had so far. But I want to make sure we have plenty of time. So in case you're curious, I've also decided I really like teaching this class in 50-minute time blocks as opposed to 75. It's just more bite-sized. You know, I really like it. I'm going to see if I can keep doing it Monday, Wednesday, Friday. Anyways, so we talked last time mostly about fats and oils and triglycerides, certainly, and soaps. That was mainly what we concentrated on. There are a couple other classes of lipids or fat-soluble molecules that are closely related to triglycerides. And that's what I'm going to get to next. I also just want to say as kind of a side note, since what I'm planning on doing is at first here I'm going to be drawing on my whiteboard like usual. Then I'm going to switch over to your chapter 15 class notes because all of the structures I need are already in your class notes. One of the, I think the last class of compounds we're going to cover today is the broad general class of those molecules that are related to steroid hormones. So they would be your cholesterol, sex hormones, cortisone falls into that category, bile salts fall into that category, and all of them have a certain ring system in common, which I just thought I'd quickly sketch over here. It consists of 4 rings of a particular size and fused together in a particular way. And it looks like this. It's always 3 6-membered rings and 1 5-membered ring fused together like this. This is, they call this the, they call that the steroid nucleus or the steroid framework. And you will see when we get there that all of the molecules we'll be talking about will have that tetracyclic, that 4-ring system in them. Also, just by way of adding some context to any past or future biology or biochem material you might have covered, they refer to these rings by letters. They call this first 6-membered ring the A ring, this is the B ring, the C ring, and the 5-membered ring is the D ring.
He's never played a full season.
So, ooh, I forgot to mute.
To grow him.
Knew I forgot something.
Like a full 82 games.
I didn't understand that, which might be just as well, since you all laughed. I don't mind being outside the joke this time. Anyways, so we were talking about the steroid nucleus, the A, B, C, and D rings. Did I have anything to add to that? I don't think so, but in particular later on, I'm going to be referring to the A and B rings when we talk about bile salts. So I just wanted to get this general structure up for you because all of those compounds will have that in common. Cholesterol has this kind of structure. The sex hormones have this kind of structure. So they're all going to be related to that. But I wanted to get it up there on the whiteboard now, even though we're not covering it, because this is the only time I'm going to be writing on the whiteboard, if that makes sense. So let's see, couple other types of lipids that are related to triglycerides. Maybe we'll just refresh our memory on what those look like. I did it again, wait. I think I see what my problem is. One, two, three propane trial. Why am I having so much trouble with this? Yeah, I see what I mean, you can draw it this way too, but I think I want to do something more like this. You can draw it the other way too. It's certainly not wrong, but this is a triglyceride. Another closely related material, closely related compound is the phosphatidate. Phosphatidate. And a typical phosphatidate looks just like a triglyceride, except that one of these carboxylic acid esters is replaced with a phosphate ester. And I don't believe it even matters which one. It could be any one of the three. It's supposed to be a lone pair. I'll add lone pairs to the oxygens that have a non-zero formal charge. So that's a typical phosphatidate. We're just replacing one of the carboxylate esters with a phosphate ester. And we're familiar already with phosphate esters from the chapter on nucleic acid. So that's not the first time you've seen that functional group. So that's what we call a phosphatidate. And then phospholipids are also related to that. A phospholipid starts out the same way. You'll have a triglyceride and you'll still have two of the carboxylate esters there. And you'll again have a phosphate ester, but the molecule continues for a little while. There is other spinach attached. A typical phospholipid will have a couple of CH2s and then some kind of quaternary ammonium species, looking something like this. So this is not the only phospholipid, but they all look something like this. They have, one of the carboxylate esters is replaced with a phosphate ester, followed by some CH2s, and then some kind of pendant quaternary ammonium salt. That's very typical. And again, I'm no biologist. You guys probably know more about this than I do. But my understanding is you find phospholipids in cell membranes. I remember something about a phospholipid bilayer. And they speak of the polar end, which would, of course, be the quaternary ammonium salt that has a full +1 charge on it. So that's quite polar. And then the rest of the molecule is comparatively non-polar. And so that's how the molecules will line up with all the polar ends facing one direction towards the aqueous system, and then all of the non-polar parts also facing in the same direction. That will be I guess you would call these the hydrophilic and hydrophobic ends, respectively. Hydrophilic, water-loving; hydrophobic, water-hating, or water afraid of water. So these parts of the molecules are, especially, remember, those R groups are going to be really, really long hydrocarbon chains that may or may not have double bonds incorporated into them. So the R groups are very, very long. So they're going to be extremely hydrophobic and extremely lipophilic, Meanwhile, this part of the molecule will be quite water soluble. It's an ion. It's like sodium chloride, like the sodium ion and sodium chloride, only bigger. So that's what a typical phospholipid looks like. And the way you distinguish it from phosphatidates is, again, by the presence of this pendant quaternary ammonium salt. That's what I would always look for. Absent that, it's a phosphatidate. But both of them are very closely related to triglycerides. So I think that's really all I need to say about that. Let me just make sure I'm not missing anything. Good. Any questions on any of this? Well, I'll leave that up there in case I want to draw later, but I figured I would switch over to the notes since I have all of the structures in there already, and none of us really wants to spend the time drawing all these big molecules out, but I did already include all of the structures in your class notes. Good. So next class of lipids I want to go over is prostaglandins, and there are some compounds closely related to those as well. And again, I certainly would never ask you to memorize a particular prostaglandin. I would never say, like, draw prostaglandin E1. Certainly not. I don't have it memorized. I wouldn't expect you to either. But I think if you analyze this molecule, knowing what we already know about organic chemistry, you'll agree there's nothing too terribly complicated here. It basically looks like a fatty acid. Here's your carboxylic acid group. Here's your long alkyl chain. Interestingly, it has a trans double bond in it. I don't know if they always do. There may or may not be OH groups along the way like that. This is just one example of a prostaglandin. But it seems to me that all prostaglandins always have this 5-membered ring fused onto it, somewhere in the middle of what would otherwise look like a fatty acid chain. And that 5-membered ring may or may not have a ketone functional group. It may or may not have an alcohol. It may or may not have other functional groups on the 5-membered ring. But in any case, you're going to find a 5-membered ring. And prostaglandins are involved in pain and inflammation responses. That's my understanding. I believe when you take your over-the-counter NSAID or non-steroidal anti-inflammatory drugs, your aspirin, your Advil, your Aleve, all of these types of things, I believe it's prostaglandins that they go after, and making sure that they are diminished or something like that. Again, I am not a biochemist, but that's my understanding of the situation. So that's what I would look for if you're trying to tell whether something's a prostaglandin. Your book also goes over leukotrienes and lipoxins. Those lack the 5-membered ring, and I certainly think the 5-membered ring is what makes prostaglandins stand out. I'm certainly not interested in writing trick questions. I try my best not to. I fear I sometimes succeed in doing it anyway, even though I try not to. But they are certainly related to prostaglandins. I think that's a fair statement. So we've already covered waxes. That just leaves terpenes and the broader class of steroids. And then we'll be done with lipids. And as I thought, I could probably have fit this all into one lecture, but you know me, there's a sense in which I want to push you guys and I want to challenge you guys, but I also don't want to be the guy that's going 95 miles an hour all the time. And I don't mind slowing down and splitting it up into manageable chunks. So, but terpenes are another class of lipids. And again, let's not forget what we mean by lipids. We're talking about molecules that are going to be, by and large, water insoluble. In fact, they're going to be fat soluble. So that means they're going to consist largely of nonpolar hydrocarbon. And I think you'll agree that's pretty much what we've seen so far. Certainly triglycerides with these long R groups over here are going to be overwhelmingly fat soluble. Same thing with these others. Look at all of the hydrocarbon in the steroid framework. And yes, give or take an occasional ketone or alcohol functional group. Pretty much no matter what we do to this, we're going to wind up with something fat soluble. We said the same thing about waxes. We said the same thing about soaps. although they have the double life. They like phospholipids of a polar end that's water soluble and a non-polar end that dissolves the dirt. By the way, I know one thing I forgot to say about waxes. I don't mean to get gross, but I know it will have come to people's minds. What about earwax? Earwax is different. Earwax, I think, is water soluble, or at least slightly water soluble. So that's not the same thing as beeswax or something like that. I don't. So anyway, I just thought I'd say. Oh, and another thing I realized I forgot to say. Just in case you're curious, and your exam grades already reflect this, there was one question in this exam that I threw out because I noticed there was a misprint. So I just didn't count that question, and you guys all got credit for it. So that's already factored into your raw score, just in case you were wondering. So I'm glad I noticed the misprint too. I mean, it's only one question, but I do want it to be correct. So certainly prostaglandins are also going to be overwhelmingly fat soluble. Terpenes are the same. These are molecules that are built up of 5 carbon pieces. And a typical monoterpene includes 2 of the 5 carbon pieces. So a monoterpene has 10 carbons in it. But the 5 carbon piece is known as isoprene. Now, you're not going to actually find isoprene just like that in living systems. It's kind of toxic. But if you start attaching enough phosphate groups and things like that to this, then you start getting a molecule that your body knows how to deal with and can incorporate into larger molecules. So a typical monoterpene will have 10 carbons in it, consisting of 2 of these 5 carbon isoprene units. And it's usually fairly easy to pick out where the isoprene units are, because you see how isoprene has this carbon atom sticking out here, that methyl group over there. And you can see carbons sticking out along the chain, like here in myrcene. You can see that there's carbons that are sticking out. So you can almost count the 5 carbon units, 1, 2, 3, 4, 5. Here's one, and the other 5 will be another isoprene unit. And then in citral, the same thing. Here's 5 carbons, and here's 5 carbons over here. You'll probably get a chance to practice doing that in the OWL assignment. I left a couple questions like that, and they're kind of fun and usually not that difficult. Menthol, which you'll have heard of, is also a monoterpene. It is 10 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can see here's a sticky outy piece over here that comes from one isoprene unit being over here. And the other isoprene unit would include this part of the molecule. So you again have the little sticky outy part over here. So these are examples of monoterpenes. There are also sesquiterpenes and diterpenes, and you can even go up to triterpenes. It even goes more. Sesquiterpenes, that prefix sesqui is not something you run into every day, but the prefix sesqui means 1.5. So a sesquiterpene will contain 15 carbons, 1.5 monoterpene units, and thus will have a total of 15 carbons, whereas a diterpene will have 2 monoterpene units. 2 times 10 carbons is 20, and it will come from 4 5-carbon isoprene units. So the main thing you need to know is that these all fall under the general class of terpenes. And when you talk in particular about monoterpenes, you're talking about a compound with 10 carbons, 2 5-carbon isoprene units. And then sesquiterpenes like farnesol, of course, I don't ask you to memorize these compounds, but I would expect you to count this out and say there's 15 carbons. Not only that, I can see 3 sticky outy bits over here that look like they come from the methyl group in isoprene. So this would probably be a sesquiterpene. It contains 1.5 10 carbon units made of 3 5-carbon isoprene units. And likewise, this one over here, this one, if you count up the carbons, you'll find there are 20. It's also pretty easy to see 1, 2, 3, 4 methyl groups that stick out. Those are going to come from the methyl groups in isoprene, most likely. So this is going to consist of 4 isoprene units. 4 times 5 is 20. It consists of 2 10-carbon terpene units. So we call it a diterpene. And so I would expect you to be able to know that much. I would never say draw vitamin A. No way. But I would expect you to know that that's a diterpene. Also a fat-soluble vitamin. And that's another topic also, the difference between fat-soluble and water-soluble vitamins. I would never ask you to distinguish between a diterpene and a fat-soluble vitamin that happens to be also a diterpene. I think that's kind of a dirty question. But that being said, it's pretty easy to see that a molecule like this is going to be very water insoluble. Yes, it does have this one OH group that will be able to undergo hydrogen bonding with water, but then you have this huge hydrocarbon portion that's actually going to interfere with the ability of the OH even to undergo hydrogen bonding. It probably can a little, but the vast majority of this compound, I think you'll agree, is overwhelmingly lipid soluble, not water soluble. Meanwhile, if we were to look up the structures, we'll get out Google. Let's look up the structure of vitamin C. That's an example of a water-soluble vitamin. There we go. There's vitamin C. Well, you know, just look at all those OH groups. Look at this polar ester group over here. That definitely looks like something that is going to be water soluble. And so vitamin C, I don't care if you memorize the structure, that's not the point. But my point is that that it's pretty easy to tell a water soluble vitamin from a fat soluble vitamin. Let me do one more. The B vitamins are also water soluble. Let's do maybe vitamin B12. That was a little bit more complicated than I thought. I didn't realize it would have the the porphyrin included in there. What about vitamin B6? Although, I mean, we can even handle that. Just look at all of these OH groups, look at all of these amide functional groups. That certainly looks to be water soluble. I just didn't expect the porphyrin in there as well. Let's look up vitamin B6. That's a little bit easier. So, sorry? We'll go back to that and you can compare. But again, you've got a pyridine, and we already know from the heterocycles chapter, pyridine is water soluble. In addition, you've got an OH group plus this phosphate over here that's pretty water soluble. So no big surprise that that's a water soluble vitamin. And if you compare structures like that to the structure of vitamin A, which is all hydrocarbon, there is no way that's going to be water soluble. You have this one OH group, but the overwhelming majority of the molecule is hydrocarbon. So I wouldn't expect that to be water soluble. Is that what you were asking about? Yeah, so I think the difference is pretty clear between water-soluble vitamins and fat-soluble vitamins. And you can correct me if I'm wrong on this, but my understanding is that the water-soluble vitamins, not that I would go eating whole bottles of them, but they're much less dangerous because I don't want to be indecent, but we eliminate them very quickly and very easily. The fat-soluble vitamins you can overdose on. That's my understanding. So you want to watch those. They get into your fatty tissues and it's much harder to get out the excess. So you want to be careful not to take too much of those. You want to get enough, but not too much. Good, and that leaves us with our last class of compounds, which will be steroids, cholesterol, sex hormones, cortisone, things like that. And I showed you at the beginning of the class the 3 rooms in a garage, the tetracyclic framework. I saw it called that somewhere, 3 rooms in a garage. I thought that was pretty clever. But all of these have that tetracyclic system in common. If you were able to recognize cholesterol as opposed to any of the others, I'm not seeing any of the terpene examples from my screen. Oh, you know what? I'm sorry, those of you in chat, I forgot about that. I forgot to do new share. There you go. Now you should be able to see it. I apologize. Let me show you where they were, but they are in the class notes. There's the prostaglandin that I was talking about. And yeah, you see, now I can see the green border around that. Here's some of the monosesqui and diterpenes that we talked about. And now we're getting to the steroid hormones. So cholesterol is over here. I always look for the OH over here coming off of the A ring, and this weird alkyl group. I'm sorry, yeah, this weird alkyl group coming off the D ring. That's what I usually look for. I don't have cholesterol memorized, but it might be one that wouldn't be bad to be able to recognize. I don't say memorize, but I think that could be useful information. It might be something you've talked about in past classes also. But one interesting thing about cholesterol, we did a chapter in stereochemistry and we talked about chiral carbons. Cholesterol is 8 chiral carbons. I might have made this point before, but it's so incredible. I think I'll make it again. So remember the 2 to the n rule. That says for n chiral carbons, you've got a maximum number of 2 to the power n stereoisomers. So 2 to the 8th power is 256, meaning besides this structure that you see here, there's 255 other stereoisomers, but only this one stereoisomer out of all 256 of those compounds is biosynthesized. I think that's just incredible about how selective the chemistry of living systems is to be able to churn out a molecule with that much complexity in it. But these other ones, we've got a few sex hormones over here: progesterone, testosterone, and estradiol. Estradiol is interesting because it has the A ring is aromatic, so that's allowed. But of course, I don't expect you to memorize any sex hormones. I would never say which of the following is testosterone. No. But if I gave you testosterone, I would expect you to say, well, that's not cholesterol, and it's also not a bile salt. It must be a sex hormone or something like that. And it's certainly not a terpene. It's not a triglyceride. It's not any of the other ones that we talked about. That I would expect of you. But no, I certainly do not expect you to memorize these complicated structures. Cortisone is another compound you've probably heard of. It might be that either you or a family member has had cortisone shots. So there you go. That's cortisone. I am no medical doctor, so I don't really know how it works, but my understanding is they inject it into people's joints when they're giving them problems. The last class of compounds related to these is bile salts. And I would like you to be able to recognize a bile salt, though again, I don't expect you to memorize particular ones. Bile salts are also called bile acids, same thing. But what you want to look for is between the A and B rings. If you see a cis ring fusion there, do you see how the methyl group and the H are cis to one another? They both have wedge bonds. If you see a cis ring fusion there, you're looking at a bile salt. If you do not see a cis ring fusion, then it is not a bile salt. And that could be either because the ring fusion is trans, one up, one down, then you don't have a bile salt. Or the other thing you might have that you'll see in actually all of the 5 other compounds is the ring fusion is neither cis nor trans because one of the 2 carbons is sp2 hybridized. So there's no cis-trans distinction. Right over here at this carbon, it's flat. Same thing with estradiol, they're both sp2 hybridized. So there is no cis and trans, it's just flat there. Likewise, in testosterone, we have an sp2 hybridized carbon, same thing in progesterone, same thing in cholesterol. So there's no cis-trans distinction. But if you do see a cis ring fusion there, then you've got a bile salt. And that much I would expect you to recognize. Though, like I said, you certainly do not have to memorize any of these structures as such. That I think would be a little bit beyond the pale. Good. So I think that's all I've got on lipids. Any questions on any of that? Looks like we're gonna, I do still want to, if you'll indulge me, a little embarrassed letting you out 15 minutes early, 10 minutes I could live with, or 12 minutes even. If you'll let me ad lib a little bit on alcohols just to get us started on them. But yeah, all of those structures starting with with prostaglandins, those are already in your class notes. So it was just the ones in the beginning were smaller compounds and I didn't mind drawing them all out. Good, so I think that's all we need from your class notes. Let me go back to the whiteboard in case I need to write anything. Good, so alcohols, I think you know what alcohols already are. Alcohols are organic derivatives of water. They are molecules of this type, where R, of course, cannot be hydrogen, because if R is hydrogen, you've got water. Water is inorganic. Seems strange to call water inorganic, but it is. There's no carbon in it. Yes. Organic derivatives of water. So are ethers, by the way. Of water, as are ethers. So they're all of that general type. R can be pretty much any alkyl group. R can also be a benzene ring, in which case you get a phenol. We've already learned how to name phenols, and we'll talk about them more in this chapter as well. Phenols are alcohols, but they're special. They have some unusual properties that we'll get to. And that's really what we're going to talk about mainly in this chapter. We're going to talk about the properties of alcohols. We're going to talk about ways of making alcohols, some of which we might know already. We're going to talk about reactions of alcohols, some of which we might know already, but it's going to focus on alcohols. And the reason you need to know this material is because alcohols are very central in organic synthesis in any other field that touches organic synthesis at all. Any of the pharmaceuticals fields, again, pharmaceuticals for either humans or animals, are often made starting with alcohols because there's so many reactions that alcohols can do, which is probably why we're doing 3-fold class days on it. But alcohols give you lots and lots of possibilities, as opposed to, say, alkanes, which don't really undergo a lot of reactions. They're quite inert. With alkanes, you've got halogenation and combustion, and that's about it. There really is nothing else. Alcohols are very synthesis-friendly functional groups. They offer lots and lots of possibilities. And so that's, I think, what we're mainly going to talk about. But other things I could say about alcohols, like how they're polar or undergo hydrogen bonding, I can leave all that for our first actual lecture on alcohols. But alcohols are a critically important functional group. They play a very central role. And with that, I am out of material. So I suppose I will let you guys go for today. I do want to push you, but I don't want to push you too hard, especially when we're out of material. I'm not going to BS you. We're done. So have a great day. I will see you all on Wednesday.